Let's welcome our guest, Bharat Ratra, distinguished professor at Kansas University, who was one of the pioneers in approach to the dynamical dark energy and is known for his work regarding inflation and its different aspects. Many of you were yesterday in the public lecture, but today we will be talking more physical stuff. So I think we will enjoy it.
Thank you very much. It's great to be back again. So today I'm going to talk about a little more technical stuff and the geometry of the universe and what kind of dark energy we might have. And so I want to start with the contributions to the energy budget now at the present time. And these ratios change because as you go back in time, things evolve. So we know that 5% of the stuff out there is atoms and molecules and some charged particles like electrons, and cosmologists refer to this as baryonic matter. And this was first kind of proposed, realized by Gamow and his postdoc and graduate student in the 1940s when they were trying to make the light elements, and they realized there'd be microwave background photons left over. And these photons were discovered by accident by Penzias and Wilson, and the interpretation of their measurements were given by Dickey and people in a companion paper. And so this number got pinned down in the mid or late 1960s. Even more earlier than that, in the 1930s, Zwicky was looking at collections of galaxies. These are clusters of galaxies. And he could measure how fast these galaxies were rotating around each other. And from those speeds and the assumption that gravity was creating those motions, he figured out how much mass he would need to produce those speeds. And he realized that he needed much more mass around than could be accommodated in the shiny stuff in the stars and in the hot gas. Excuse me. And so he had discovered dark matter, and the speeds he was looking at were a few hundred to maybe 1,000 kilometers a second, which are really slow compared to the speed of light. So that kind of speed is said to be non-relativistic or cold. And in the 1930s, he didn't know that only 5% of the stuff was made up of atoms and molecules. But in the 70s and 80s, people realized that what Zwicky had originally seen was not made up of atoms and molecules. So it's called non-baryonic cold dark matter, and that makes up about 25% of the stuff out there. And even more recently, we've discovered something even stranger, which has been called dark energy. So it's called energy because people want to distinguish this from matter. It's not energy in the sense of electromagnetic energy or kinetic energy or chemical energy, but it's just a different name for a substance that's not matter. And if it was made up of particles, those particles would be moving at speeds close to the speed of light, and so it's relativistic. And it's also not made up of atoms and molecules because atoms and molecules make up a very tiny fraction. It's the biggest contributor to the energy budget now. This is from about 70%. 25% is dark matter and 5% is ordinary matter. So we basically don't understand most of the stuff out there now. 95% of the stuff out there, but we do have a standard model for cosmology that works pretty well. So I want to start by motivating dark energy, and then I'll look at a few models of dark energy, the standard model where you have a lambda, a cosmological constant, and cold dark matter, and a model where you can make lambda a dynamical field, a scalar field phi, and that's called phi CDM. And then observers use parameterizations for dynamical dark energy instead of working with this model, and that parameterization is usually called XCDM, where you have an X fluid. And we'll look at these models. I'll talk about them a little bit and then make predictions using them and compare those predictions to a bunch of different cosmological observations. And the models are parameterized with 3 or 4 or 5 or 6 different parameters. And by comparing to measurements, you can constrain those parameters. And we'll look at how you can constrain them. And then we'll look a little bit at the transition from the present time, where the cosmological expansion is accelerating, to higher redshifts where it was decelerating. And I'll also talk a little bit about the constant, the value of the Hubble constant, and maybe if we have time, we'll talk about the geometry of space. So this is the general idea. We have a lot of good cosmological data, but it's not good enough to give you model-independent constraints. So if you look at high-energy physics experiments, there's a lot of experimental data, and you can get model-independent constraints, but in cosmology, we're not at that point yet. So we want to try to use a model, and preferably a physically consistent model that you can parameterize with a few parameters, and then use your data to constrain those parameters. And that gives you tighter constraints on the parameters, but they're going to be model dependent. And then the way you look at this is you use a whole bunch of different models and see if you can get the same region of parameter space using these different models. And if you do, then you're pretty happy and your conclusions are pretty general. If you don't, then either one of the models is ruled out, or there's some systematic effects in the data that you haven't accounted for properly. And you can also use these models to combine constraints from many different data sets. So we talked a little bit about this yesterday, that the universe expands, and that means that if you have a wavelength or a proper distance, that's going to grow with the scale factor. And one way to look at this is in terms of a closed universe, a one-dimensional closed universe, which is the circumference of the circle. And this is it at an early time, this is it at a later time. And I'm going to take the radius to be the scale factor. So as time goes on, A gets bigger. And the circumference is going to be 2 pi times the radius. So the circumference also gets bigger. And it gets bigger in direct proportion to the radius of the circle. And I've put a wave on here. And we can kind of think about this being an electromagnetic wave, maybe in the visible part of the spectrum. And then its wavelength, or its time period, is of the order of a femtosecond. And the expansion time scale is going to be much, much bigger. It's roughly 13 or 14 billion years. And in terms of seconds, that's an exasecond. So the scale, the difference between the time period of this wave and the time period associated with the expansion of the universe is more than 30 orders of magnitude. And in a situation like this, where you have 2 different time scales, one associated with the wave that's very, very fast, and one associated with the expansion that's very, very slow, you have an adiabatic system, and you can't pump energy from the electromagnetic wave into the expansion of space or vice versa. And so your only option is that the number of zero crossings remain the same. And for that to happen, the wavelength has to get bigger as a function of time. And it's pretty easy to see it gets bigger in proportion to the scale factor. And from this, you get Hubble's law for this uniform expansion, where the recession velocity is proportional to the distance. So a galaxy twice as far away would move twice as fast, and 3 times as far away it would be moving 3 times as fast. This constant of proportionality is called the Hubble constant. And because astronomers have strange conventions, they measure distances in megaparsecs, and they measure speeds in kilometers per second. The units of this are going to be kilometers per second per megaparsec. But you can see dimensionally the Hubble constant has units of 1 over time, because this is distance over time, that's distance. And so the Hubble constant is roughly 1 over the age of the universe, if you ignore the expansion of the universe. So my favorite value of the Hubble constant is around 68 kilometers per second per megaparsec. And sometimes, because it was the error bars used to be much bigger, people would write this as 100 small h kilometers per second per megaparsec, and then at the end of your calculation, you could pick whatever small h you prefer, and if you want 68, it would be 0.68. And this law actually holds at all times, because you can go back to this, and you can go and put a smaller circle here or a bigger circle here, and as long as you have uniform expansion in space, then you get a Hubble-like relation. But the constant of proportionality is going to be different depending on what time or what redshift you look at it. And so that constant is usually called the Hubble parameter, and it's a function of redshift, and the value of the Hubble parameter at the present epoch is called the Hubble constant. So this is the same plot I showed day before yesterday. This is the results of the Hubble Space Telescope Key project in 2001. And the velocity, recession velocity is here, the distance is over here, and this straight line is the Hubble law. The distance, the recession is proportional, the recession speed is proportional to the distance. And the slope of the straight line is the Hubble constant, and then it was 72. Now my favorite value is around 68, which is not that far from 72. And most recent estimates agree with this thing of being around 68. There are some exceptions, but microwave background agrees with this, and baryon acoustic oscillations agree with it, and so do many other measurements. Okay, I'll skip this and we can come back to that later if there's interest. So we have this expanding universe, and we have to be kind of careful because not all observers are going to see that it's isotropic. You can think about the balloon on Saturday. So if you start moving on the surface of the balloon, you're going to see differences in front of you and behind you. You'll see the Doppler effect. And so it's only those observers that are sitting on the surface of the balloon that don't see the Doppler effect. And those guys are special observers, and they're called cosmological observers. And it's conventional to assume for these guys that the cosmological principle is valid, that the universe looks isotropic for all cosmological observers. So on large scales, it looks the same no matter what direction you look in. And then because you're translating yourself, so if you think of yourself as being on the Milky Way and looking around and it looks isotropic, and then you translate yourself to Andromeda and look around and it looks isotropic, then it's easy to see that you have to be in a system with much more homogeneity, much more symmetry, which is a homogeneous system. And so an isotropic system from 2 points in space implies that you have a homogeneous system. And an example of a homogeneous system is milk in a container. So no matter where you are in that container, that milk looks equally white as long as you don't get to the edges of the container. And that system has much, much more symmetry. And you can use the symmetry to restrict what spaces you allow. So we live in a three-dimensional geometry. So it's here, there's the vertical axis, there's the two horizontal axes, and it's a three-dimensional spatial geometry. And it's going to be difficult for me to draw these geometries, so I'm going to suppress them, and instead of talking about a three-dimensional volume, I'm going to talk about things like the top of the table, which is a two-dimensional flat space, and it's got to go out to infinity in both dimensions. So once you restrict yourself to homogeneity, you have only three possible geometries: the flat ones that I just talked about, and the open and the closed ones. And these are the geometries with one dimension suppressed. So if we start out with the flat geometry, it's going to go out to infinity in both dimensions. And if it doesn't, you could go to the edge and look out, and it wouldn't look the same when you're looking in, so it wouldn't be isotropic. So that's the flat geometry. And for those of you who know general relativity, here's the scale factor, the line element up here. And these are the spatial scale factors that show up over here. It's the three-dimensional part of the metric tensor. And the spatial curvature in the flat case is 0. So you could also live on a two-dimensional positively curved space, like the surface of a balloon, and you can't go in or out. There's nothing inside or outside. It's just the two-dimensional surface. And you can specify any point here with a latitude and a longitude. This is called a closed geometry, and the space curvature is positive. K squared is greater than 0. And just like you have a positive curvature, you have a negative curvature surface, a constant curvature. And that's the saddle shape, and it's got to go out to infinity in both dimensions. And the curvature is negative. This is called an open geometry. And there are these symbols up here, and I'll define this in a second. This is the Greek letter omega, and it's the density in a strange system of units to make it a little bit easier to write. This is a critical density geometry. This is an overdense geometry, and this is an underdense geometry. And for those of you who know GR, that's the scale factor for the spatial part, and you can think of that as the radius of this balloon, and as time goes on it gets bigger and bigger if you're looking for the expanding solution, and that's your dynamical variable. And it's pretty much like any dynamical variable in physics, you need equations of motion for it. And you can think about what we do for the harmonic oscillator. So for the harmonic oscillator, you have a mass and spring system. And if you displace that mass away from equilibrium, that distance from equilibrium is your dynamical variable. And you can write down ma equal to F. And if you choose for the force, you choose Hooke's law, that's minus kx. So you have mx double dot equal to minus kx. And that's your equation of motion for the harmonic oscillator. But you can also integrate that once and write down 1/2 mx dot squared plus 1/2 kx squared equal to a constant. That's the energy. So that's the first integral of Newton's second law of motion. And what I'm going to write down here is the first integral, the equivalent of the energy equation. And I'm going to use ideal fluid approximation for the matter, for the baryons, and for the cold dark matter, and for the cosmological, for the dark energy also. So a dot here means a time derivative, and A is the scale factor. So A dot is the rate of change of A. And this is the amount of energy in the expansion of the universe. It's also equal to the Hubble parameter. So H is equal to A dot over A. And so H squared is A dot over A squared. And on the right-hand side, I'm going to write down all the forces that drive, all the terms, the energy terms that drive the expansion. So we know it's coming from gravity, so we're going to have a big G. And so we could, in principle, be looking at an infinite universe in 3 dimensions. So if you're looking at the mass, which causes the gravitational field there, that mass, that total mass is infinite, and it becomes really difficult to work with infinite masses. So what we're going to do is we're going to look at little patches of the universe, and we're going to look at the mass density, because that's going to affect how space changes because of gravity. And so this is the mass per unit volume, that's rho. And G is Newton's constant for gravity. And so this tells you that if you have some mass, you're going to have some energy here that drives the expansion. You can also get some energy that comes from the curvature of the space. And because the curvature contributes at 1 over A squared, 1 over the scale factor squared, that shows up over there. And we also have a cosmological constant that doesn't change with time. So we might think that we can go ahead and integrate this equation just like we could do for the 1/2 mx dot squared plus 1/2 kx squared equal to a constant. But we can't, because rho changes with time, and we need to know how rho changes with time. So from the stress energy conservation, we can get an equation of motion for rho. And that tells you the rate of change of rho is proportional to rho plus the pressure. And I'm writing this in natural units. If I was using conventional units like CGS or something, there would be a c squared in the denominator of this term. This is the pressure, and it's measuring the energy of motion, the kinetic energy. And that's very, very subdominant compared to the rest mass energy. And it's only when you start getting relativistic motion does this term become really important. And to complete these equations, we need to know how the pressure depends on the energy density. So we have these three equations, and these are the equations of motion. They're more complex than the equations for the harmonic oscillator, but that's what we have to deal with. So the first thing we know is that the Hubble parameter is A dot over A, and things are moving away from us, so A dot is positive. So the next thing we might want to find out is whether this expansion rate, whether it's increasing or decreasing with time. So whether the person who's powering the universe, whether she has her foot on the accelerator or she has her foot on the brake pedal. So if she has her foot on the accelerator, she'd keep moving away faster and faster. If she has her foot on the brake, the car will still move, and then it'll slow down and it'll eventually stop. So you want to figure out the rate of change of the expansion. And there's an easy way to do that. You just take these equations and work with them with the calculus and get a second time derivative equation, which is very, very similar to A equal to F over M. And the equation is written over here. So unfortunately, we're using A for both the scale factor and the acceleration, so we have to be a little bit careful there. And in my case here, the double dot means it's the second time derivative, so this is the rate of change of the scale factor. It's the acceleration of the scale factor. So this guy is proportional to a kind of messy term on the right-hand side. So let's just forget about this term, and this term for now, and just focus on this part over here. So the M means matter, and this is coming from the rest mass energy. So you can think of this as a bunch of galaxies that are distributed in the universe, and that gives you the mass per unit volume. And so as you have more mass, then this gets bigger and bigger, and you have this negative sign over here. So this is what it's telling you, is you have these two effects at play. So if you have two galaxies near each other, they're going to want to pull on each other, and they're going to want to prevent Einstein's space creation process. But if you have lower mass galaxies, that space creation process can win. But as you increase the number of the amount of mass you have over there, you're going to get a minus sign over here from these equations, and that's telling you the acceleration is negative, you have deceleration. So we can go and add more stuff to this and look at galaxies that are moving, and this quantity rho plus 3p is called the active gravitational mass density. It's the real measure of the gravitational effect of any matter distribution. And you see that if the galaxies are moving relative to the expansion, the stuff in these round parentheses are bigger than just rho sub m. And so this is a larger quantity. It's also positive, and you get more deceleration. So if you're an observer, you can try to go measure A double dot. And if you do that, and people did this in the late 1990s, and what they discovered was that A double dot was positive. And that's a problem. So you have a couple of options here, because you're predicting that with ordinary matter and cold dark matter, the right-hand side, this part of the right-hand side is going to be negative. But observers who measure this find A double dot is positive. And so you can either say that Einstein was wrong and general relativity is not the correct theory of gravity, and so there's no problem, this equation is just wrong and we should ignore it. But if you're a little more conservative and say that general relativity works really well for black holes, it really works well for the microwave background to within a factor of 2 or so, that we want to try to preserve general relativity, is there some way we can fix up this equation? And one way we can fix it up is to introduce a new substance called the cosmological constant that's also got a rho. The symbol lambda is a symbol for the cosmological constant. It's got a rho, and it's also got a pressure. And we see substances similar to this in the lab when we're doing some quantum mechanical experiments. And one example of this is when you look at something called the Casimir effect, or another example is the Lamb shift in the hydrogen atom. And there you see effects from the Heisenberg uncertainty principle 0-point fluctuations, where you get a a substance that you can describe with an equation of state that's P equal to minus the energy density of that substance. So if we have a similar substance on cosmological scales and we give it the name the cosmological constant if it has this equation of state, then when you look at this, you have 3p here, 3p sub lambda, and p of lambda is minus rho of lambda, so this is minus 3 rho of lambda. So rho lambda minus 3 rho lambda is minus 2 rho lambda. So everything in the round parentheses here is negative if rho lambda is positive. And so if you take rho lambda to be bigger than rho matter, then the negative part in here can overwhelm the positive part in here and make everything inside the square parentheses negative. And that negative sign will cancel this negative sign to give you a positive sign to be consistent with the positive acceleration that astronomers measure. And so that's why we're introducing dark energy to agree with the observations, to make general relativity agree with the observations and have accelerated expansion. So this parameter omega that I'd shown you before here is just defined this way. I mean, you can just take this as a definition. It's basically, there's a critical energy density that corresponds to some specific model here. And you divide through by that critical energy density to get omega. So this critical energy density is roughly 10 to the minus 30 grams per cubic centimeter. So it's very, very tiny. And so you don't want to use grams per cubic centimeter as your unit because you'd have to carry around many powers of 10. Okay, so we can look at how this expansion was discovered. And this is what was discovered in 1997 and 1998 with the type 1a supernovae by Rees and Smith and Perlmutter and their collaborators. So we're going to look at the Hubble law in two different models. And I'm going to plot distance on this axis and the recession velocity over here. So if we have a slowly expanding universe and we have a more rapidly expanding universe, and if we look at a galaxy, two galaxies at the same distance in these two different universes, the one in the more slowly expanding universe will be have a smaller recession velocity. It'll be closer to the origin here. The one in the more rapidly expanding universe will have a larger recession velocity. And we should remember that as we look at galaxies further back in time, it takes time for that light to reach us. So we're seeing them when the universe was younger. And if we go back to a galaxy over here, and look at them over here in these two universes, we'll be seeing those galaxies at earlier times than these galaxies. And a galaxy over here, we'll be seeing it when the universe was older. A galaxy over here, we'll be seeing it when the universe was younger. So when we go back and look at bright objects, and in the late 1990s, these were the type 1a supernovae, which were probably white dwarf stars with a binary companion. And the binary was dropping, its companion was dropping stuff on the white dwarf, and the white dwarf mass went above the Chandrasekhar limit, and it became unstable, and it collapsed, and you had this huge explosion that could be brighter than a whole galaxy for even as much as a couple of weeks. So you want to have really bright things because you want to go very, very far back in time and measure the expansion rate then, and compare it to the expansion rate now and see whether you have accelerated expansion or decelerated expansion. So as you go back and look at galaxies further and further away from you, excuse me, there are three options. You could have this purple line, which has a constant slope and the same expansion rate at all times. Or it could be in the past that the universe expanded more slowly, like the blue universe over here. And as it got to the present, the slope changed closer to the green universe slope. And so you have an accelerated expansion. Or it could be that in the past, the expansion was more rapid. And then as you got closer by, the expansion slowed down. And so you had a decelerated expansion. So this is accelerated, that's decelerated. And so all you have to do is go and measure the expansion rate as a bunch of times and see whether you're bending up here or you're bending down here. And people did this with the supernovae in the 1990s, and they found most of them were on the blue part of the curve, and that you had this accelerated expansion. So this is the discovery of dark energy. So it comes with the fact that you want Einstein's general relativity to be correct, and Einstein's general relativity would not be correct if you didn't have a cosmological constant, and so that's why you introduce a cosmological constant of dark energy. And some of you might have seen plots like this where you try to use the supernovae data to constrain how much lambda you have and how much matter you have, which is baryonic matter and cold dark matter. And if you didn't have any lambda, all your points should lie on a line right over here that's consistent with omega lambda equal to 0. But the supernovae lie in this part of parameter space. And at roughly now, it's probably a 4.5 or a 5 sigma result that they're inconsistent with 0. And they're in the accelerating part of parameter space. So if you go back to your Friedmann equation and you write the sum of all energy densities you have, the active gravitational mass densities, then you have to have something with significantly negative pressure for this equation to give you a positive A double dot. And so you introduce the cosmological constant. And this is the favored part of parameter space with a pretty significant contribution of a cosmological constant and a little bit of omega matter. So we know that there is dark energy, but we don't know much about it other than that it's there. And so you might want to ask whether it changes a little bit in time, whether its energy density is constant or it changes a little in time, or whether it varies a little bit in space. And there's a bunch of assumptions. So we're assuming general relativity is correct, and we're assuming that the astronomers haven't missed any systematic errors. And those are useful things to remember. So the simplest way to answer a question like this is to look at different models and compare them to observations. So I'm going to look at a number of different models, and I'll look at them at relatively late times in the past the radiation-dominated epoch. And so I'm going to show you a bunch of plots like this. So what I'm going to plot on this axis is the energy density components, and it's going to be a log plot here. And on this axis, it's the scale factor, and against it's the log of the scale factor. So we live over here, and the baby universe is back over here, or way back over here. And we're going to start with the Friedmann equation, the expansion rate equation. And in this model, we have a cosmological constant and cold dark matter. So in the Friedmann equation, A dot over A squared, there's these three terms over here. There's the matter, there's the space curvature, there's the cosmological constant. So the matter is all non-relativistic, and so it's all rest mass energy, and that's mass divided by volume. The volume expands with 3 parts of the scale factor, so the density drops like 1 over A cubed. And that's the blue line on a log-log plot. It's got a slope of -3. The orange line has got a slope of -2 because it's got 2 powers of A in the denominator. And the green line is the cosmological constant. So as you go back in time, the cosmological constant first dominates. You have dark energy domination, and then possibly you have space curvature up to here. And then at higher redshift, you have matter domination. And it looks like you have 3 parameters over here, the mass density in matter and its space curvature and the cosmological constant. But we'll see that there's actually only 2. And conventionally, the 2 parameters are omega matter at the present time and omega lambda. And this plot sort of illustrates why high-energy physicists are very upset with the cosmological constant. So you can kind of think of this guy. It's basically proportional to a rho. And so that's a mass per unit volume. And if you're doing this in natural units, length is inversely proportional to energy and mass is proportional to energy. So this guy has dimensions of energy to the fourth. And if you take the fourth root of that, that tells you the energy scale of this phenomenon. And this energy scale is a few milli-electron volts. And that's kind of disturbing to a particle physicist because it's telling you that there's this new fundamental energy scale at the scale of basically chemistry. That's where chemistry is. And it's kind of surprising that things that are happening on the chemistry energy scale are important for very, very large scales in cosmology. More recently, people have discovered that neutrino masses are around this scale. And so there's been a lot of work, including work here by Misha and Zorab, on trying to tie dark energy to neutrinos. But that's kind of a separate question right now. So one way of trying to get rid of this energy scale, it's pretty simple. So all you do is you tilt this line a little bit. So as you go back in time, if you let the green line rise a little bit, then maybe at some time way back in the past, you can get an energy scale that's much higher than a milli-electron volt. And the reason it becomes a milli-electron volt now is because as time goes on and the universe expands, this energy density drops. And that's one of the significant motivations for dynamical dark energy. So this is a parameterization of dynamical dark energy, and it's not a very good parameterization. It's called the XCDM parameterization. To make life a little bit simpler, I've set the curvature to 0, so we're looking at this in a flat universe. And then in the Friedmann equation, you get the contribution from ordinary matter and cold dark matter, and that again goes like 1 over 8 cubed, and it's, the blue line drops like, we've got a slope of -3. And we introduce a new fluid, which I'm going to call X, and this has an equation of state P equal to small omega sub X, rho sub X. And it turns out if this equation of state parameter is less than -1/3, you can get this to give you accelerated expansion. And you can integrate the energy, stress energy equation to get this going like rho sub X going like 1 over 8 to the 3, 1 plus omega X. So you can get this sloping downwards. And again, you go from decelerated expansion where the matter dominates to accelerated expansion at the present time. And the two free parameters we use to characterize this model are omega matter at the present time and small omega sub X. The problem with this is with a little bit of work you can show that an equation of state where W sub X is negative is unstable, and this universe kind of becomes really bumpy. It doesn't look like anything like ours unless you choose to fix the rate of change of pressure with the energy density to be positive, and that's extending this parameterization and introducing one extra parameter. You can do this in a simple physical model where you introduce a scalar field and with a potential energy density. So in that case, again, I'm going to make this spatially flat to make it simple. The Friedmann equation has the matter contribution, both the cold dark matter and the baryonic matter, and that's the slope of -3 line. But you also have a scalar field with an energy density, and that guy has a kinetic energy density. It's phi dot d phi dt squared plus some potential energy density. And I've chosen a pretty particular form for this potential. It's also pretty strange. But because this is a dynamical variable, you now have to have another equation for the scalar field, which is the Klein-Gordon equation. It's the second time derivative of phi plus the Hubble friction term times the phi dot, and the dv d phi term over here. And the motivation here is to try to get this energy to come to dominate, and with this choice of potential energy density, it does. And the free parameters here are omega matter again, and the parameter alpha that characterizes the slope of this potential. And it turns out that for this potential form or various other ones, you get an attractor solution, and this attractor solution always wants to make the phi field energy density dominate over the dominant form of energy density, which in this epoch is the matter. You could go back, it would be the radiation, and it does the same thing. So you can drop down to a milli-electron volt now from a much, much higher energy density, maybe the energy density at the end of inflation at early times, and then you get rid of having to introduce a new energy scale now to describe the dark energy. So we have these models, and we can take predictions from them and compare those predictions, and I just want to use a few observations here for illustration. So we'll talk about type 1a supernovae, apparent magnitude as a function of redshift, baryon acoustic oscillations as a function of redshift, the Hubble parameter as a function of redshift, and the growth factor as a function of redshift. And here's the general procedure for doing this. So you want to compute from your model predictions that depend on the parameters of the model. And we talked about the parameters. We can do this in the lambda CDM model, for instance. So instead of using scale factors, astronomers prefer using the redshift, which is related to this redshift z or z here, is related to the scale factor at the present time. The subscript 0 is always the present time, to the scale factor at the time when that light was emitted. And if we rewrite the Friedman equation for the lambda CDM model in terms of the redshift and the density parameters omega, you get the Hubble parameter squared is equal to the Hubble constant now, this is the Hubble parameter now squared, times the stuff in the square parentheses. So you have the contribution from omega matter, which is the baryonic matter, and the cold dark matter. And that is 1 over a cubed, because 1 over a is proportional to 1 plus z, so you get 1 plus z cubed. Curvature is 1 over a squared, so you get 1 plus z squared. Cosmological constant doesn't depend on a, so it doesn't depend on e. And this stuff in the square parentheses, we're just calling e squared. And it's a function of z, and it's a function of p, where p are the parameters of this model. And it looks like you need 3 parameters, but you immediately see that if you evaluate this equation at z or z equal to 0, then this becomes h naught squared, and the h naughts cancel out, and so you get whatever's in here equal to unity, and the 1 plus z is unity, the 1 plus z here is unity. So you have omega matter at the present time plus omega curvature plus omega lambda is equal to 1. And so you get the sum rule. And so this model only has 3 free parameters. The third parameter is always determined in terms of the other 2. And so conventionally the choice is to choose omega matter and omega lambda as your 2 free parameters, as I said earlier. So this equation, if you take the square root, it gives us the Hubble parameter at whatever redshift you're interested in as a function of your parameters p, which will be omega matter 0 and omega lambda. And it also depends on the Hubble constant, because that shows up over here, and that's where it shows up over here. So you can make a prediction at whatever redshift you want. So if you have a measurement at a redshift of 0.7, you can go to your model and make a prediction there at that redshift for every parameter value and every Hubble constant you're interested in. And then with those predictions, you can do least squareds or maximum likelihood. You make your chi-squared function, and you minimize it or maximize it, whatever you're trying to do. And that'll find you the best fit cosmological parameters, and it'll find you the ranges of these parameters. And if you're interested in how to go about this, these theses of my grad students are in archive. They kind of have nice summaries. So I'll just show you a lot of plots like this, and maybe I'll just do this for some of these models, and then we can have questions. So I'll show you the three models. This is going to be the lambda CDM model, this is going to be the X CDM model, this is going to be the phi CDM model. And these are the parameter spaces we're interested in. They're all two-dimensional. And on the x-axis, we always have omega matter at the present time for each of these models. On the y-axis, we have omega lambda for the lambda CDM model. We have small omega x for the X CDM model. And we have alpha for the phi CDM model. That's the parameter that controls the slope of the potential energy density. So there's a whole bunch of lines over here. This dashed line is the line of zero curvature in the lambda CDM model. So this part of parameter space down here is open. It's the open geometry. This part up here is the closed geometry. And this line over here at w sub omega sub x equal to -1 is the constant dark energy. XCDM reduces to a cosmological constant over here. And because we have spatially flat models here, or any model at any value of omega matter here, so it's 0.1. So over here, this point corresponds to the same point on this line. Omega matter of 0.2 corresponds to the point on this line. It's a flat line with a cosmological constant. This is a flat geometry with a cosmological constant. And over here, at alpha equal to 0, you get the flat lambda CDM model. So omega matter of 0.1 over on this point right over here is the same model as omega matter of 0.1 over here and omega matter of 0.1 over here. But as you start moving away from any of these lines, you have different models. So over here, in this direction, you have non-flat geometry. In this direction, you have dynamical dark energy. In this direction, you have dynamical dark energy also. And these other lines, the dotted lines over here, these divide you from no acceleration, zero acceleration on the dotted lines, to accelerated expansion at the present time in this part of parameter space, and decelerated expansion down here, accelerated expansion here, decelerated expansion up there, accelerated expansion here, decelerated expansion up there. And these contours are the contours you get from fitting to some type 1a supernovae. It's called the Union 2.1 data set, and it accounts for all the systematic errors they've been able to estimate. So the best fit models are the big black dot. And then you have 1 sigma, 2 sigma, 3 sigma contours, 1 sigma, 2 sigma, 3 sigma contours, 1 sigma, 2 sigma, and 3 sigma contours. So we can look at the best fit models, and we see that all of them have omega matter of about 0.3. So it doesn't matter what model you use to analyze these data. And they're all close to being spatially flat. But maybe we should back up a little bit and kind of just focus on where these contours lie relative to the acceleration-deceleration boundary. In almost all of the probabilities lies in the region where you have accelerated expansion. And it doesn't matter whether you analyze these supernovae data using the lambda CDM model or the X CDM model, the phi CDM model. But any model gives you accelerated expansion. It gives you omega matter roughly about 0.3 at the best fit point, and it gives you a flat geometry. So it doesn't matter what model you use to analyze those data. But equally important, within even 1 sigma, you have a huge amount of space curvature allowed, both closed and open. Even within 1 sigma, you have a huge amount of dynamical dark energy allowed. So the best fit models are consistent with the standard model, but other models are allowed. You can look at baryon-acoustic oscillation data, and again, you get the contours. The main point is to look at the relative direction of these contours compared to the supernovae ones. The supernovae ones go in this direction. The baryon-acoustic oscillation ones almost close to perpendicular. So we'll come back to that point in a second, but let's just focus on what the baryon and acoustic oscillations tell you. They tell you omega matter of about 0.3 and a flat geometry is good, omega matter of 0.3 and a flat geometry is good, omega matter of 0.3 and a flat geometry is good. Most of the probability lies in the accelerated part of parameter space. There's very little getting into the decelerated part of parameter space. So you can conclude from this that it's almost model independent, that you get accelerated expansion. But again, there's quite a lot of room for non-zero spatial curvature and non-zero dark energy dynamic. But it's clear that if you start combining these data sets, because of the way these contours are aligned relative to each other, if you plot the baryon acoustic ones over here and you do this jointly, you'll narrow yourself down to a much smaller part of parameter space. And I mean, we can look at other data here. This is the Hubble parameter data. And as we said earlier, the Hubble parameter data depends on the Hubble constant. And that's why I have two values here. I've been looking at the Hubble constant of 68 and a Hubble constant of about 74. And you can see just when you change the Hubble constant, the contours move maybe roughly by about half sigma, and they move by half sigma. It doesn't matter what model you're looking at. But again, most of the contours are in the accelerated part of parameter space, and they're quite consistent with omega matter of 0.3, omega lambda of 0.7, flat geometry, and it doesn't matter what model used to analyze these data. This is growth factor, and again, it's the same sort of thing, mostly in accelerated parts of parameter space. Standard model is good. And so by looking at these, the really important thing is that the constraints overlap. They're not inconsistent from the different data. And individually, they're consistent with the standard model with omega lambda of 0.7, omega matter of 0.3, but you're allowed to have time-evolving dark energy density or some spatial curvature. And the next obvious step is to do this two at a time. And the only thing that changes is that, so this is supernovae and BAO. The parameter space is smaller now because the contours are getting tighter and tighter. Again, the standard model is pretty good, but you can have space curvature, you can have dark energy dynamics, and it doesn't matter what data sets you use here in pairs. If you use the Hubble parameter, you have to account for the Hubble constant. They shift. In this model? Right over there. And you can go back over here. It's right over here. And this is BAO and growth factor. This is Hubble parameter and supernovae. This is supernovae and growth factor. So combined two at a time, they tighten up, but they're still consistent with the standard model. And they're consistent. They don't rule out time-evolving dark energy or some spatial curvature. We can look at 3 at a time and 4 at a time, but you already saw, if you just look at this guy, you need to know the Hubble constant more precisely, because if you don't, then you're kind of shifting your contours and you can't deduce omega lambda and omega matter that well. And so there's, if you use different supernovae data sets, you'd shift the contours also by about half sigma. And so there's these systematic effects that we don't yet understand well enough to do precision cosmology. But hopefully these will get pinned down in the next decade or so. And I'll look at more recent. So that stuff is from 5-6 years ago. So we can look at a few other things, and then maybe I should stop because it's been almost an hour. I don't know how much you want me to go on for.
Find some focal point.
Okay, and then okay. So we can look at a couple of other things. So there's measurements of the Hubble parameter as a function of redshift. So I'm looking at all the ones that we had. This is from 5, 6, 7 years ago. And I've plotted the Hubble parameter here divided by 1 plus the redshift. And the redshift is on this axis, so we can go up to about 2.4 or so. And these are the data points with 1 sigma error bars from various different groups of people. And these are the 6 best fit models with the 2 different Hubble constants, the 674 and the 68. And I've also shown 2 3 sigma discrepant models, the predictions. So this doesn't give you a really good view of what's happening. Fortunately, we have enough measurements here so we can bin this in narrow redshift bins. And if we do that, what we can see here is that this goes down first and then goes up. And you can actually see these in the data. These are now 2 sigma error bars in the redshift bins. At higher redshifts, we can't bin them that much because the redshift bins would be much bigger and it wouldn't be accurate. But we can see that you get decelerated cosmological expansion and then accelerated cosmological expansion. And if we look at this in the lambda CDM model, this quantity h divided by 1 plus z, there's the omega matter contribution, the omega curvature, and the omega lambda. And so as you go to smaller and smaller z, because omega lambda is about 0.7, omega matter is only about 0.3, as z becomes small in the denominator, this becomes important. And so you get the accelerated expansion here. It slopes upwards. And as you go to higher z, this becomes more important, and so you get the decelerated expansion. So we're seeing the decelerated expansion for matter dominance turning into the accelerated expansion when dark energy kicks in. And this transition redshift is about 0.75 or so. So maybe I should just probably stop here and just have, if people have questions, I'll be happy to go over them.
Okay. Thanks again for the interesting talk. And maybe we have some questions to ask.
I have more of a general question. Like in a current cosmological model, any density is time dependent, but it is like homogeneous and it's not dependent on like coordinate or space and so on. It means that the current universe doesn't have a center and it is just expanding. Is there or has there been any more or less famous cosmological model that has somehow implemented or said that taken into account the density distribution is not homogeneous throughout the space, or are there like any models?
So there's two levels of inhomogeneity. You can have really very hugely inhomogeneous, right? And maybe you're thinking about a big void or a circle, and then you're sitting at the center of the circle. And models like that you can rule out because you can, there are tests for homogeneity that you can do by looking at how the density changes as a function of redshift. But on smaller scales, things are inhomogeneous because you can just look around you. Galaxies are not homogeneously distributed, and there's a 2-point correlation function. And you can model that. You can do the perturbations and integrate the equations, the perturbed equations, and get a galaxy distribution function. And
my question was like more of a historical. Has there been like those kind of famous models in the past?
There's been lots of models, yeah. So there's the famous one. It's the Lemaitre-Tolman-Bondi model, where the people assume that you're sitting at the center of a big void, and it's spherically symmetrically distributed about you. But those kind of models are pretty much, I mean, they were around till maybe the 70s or so. but the data finally got good enough so you could rule them out. I mean, there's still some people who believe that, but they're in the minority.
Is there any sort of model like that sort of suggests that homogeneity in our region, but maybe says that beyond cosmological horizons there should be a center, and from there
so that becomes really difficult, right? Because you can only see a small fraction, and it would be very, very strange. I mean, this is the same thing with the Copernican principle, right? So, I mean, you could assume that we're sitting at the privileged position in the center of our observable part of the universe, and that if you wait long enough, you'll be able to see beyond that, and it'll look very, very different. But that would be really strange.
Other questions?
I noticed a mistake in this equation. Is concern of the omega lambda. It should be divided by 1 plus z in the power 2.
No, I've taken the square root, right? Oh, no, you're right. Yeah, maybe there's an extra factor of 1 plus z. I should go back and take a look. There's maybe a typo there.
A typo?
Yeah.
Yeah.
Thanks.
What is growth rate and how do you estimate growth rate?
So growth rate, one way to estimate it is to look at spheres, and the typical way they look at it is spheres of 8 megaparsec diameter, and you integrate up the mass in those spheres and divide that by the average mass. And that's growing as a function of time. So it's the universe just becomes more and more inhomogeneous as time goes on.
Other questions? I have one question.
Yeah.
So recently there were many discoveries when they found that in the galaxies, dark matter and luminous matter, their ratio is quite different from one galaxy to another. Because if we expect it to be somewhere like 20% for visible matter to the dark matter ratio, yes? When we look at certain galaxies, mainly we should see the same ratio, do not we? And if it is not the case, yes, and we everywhere assume that this is the case, yes, because we took 30% of the matter where dark matter is also included. Will it affect the universe evolution drastically?
So you probably aren't going to get exactly the same ratio from galaxy to galaxy because, I mean, you have different formation histories, right? So if you have a small galaxy and maybe a supernova goes off in there, I mean, that supernova can blow away a lot of the baryonic matter because that light will interact with that and it won't affect the dark matter that much. So, I mean, so in the models you have, you kind of form these dark matter potential wells, and they have subhalos in them, and there's no reason to have exactly the same dark matter density in each of those subhalos. It could be slightly different, and they'll pull in baryonic matter, and you'll get some distribution, but it should be distributed with some dispersion. It's not going to be completely identical.
Oh yes, they will not be identical, but not from 1 to 100 and
right, not for, so it just depends on the
yes.
range, yeah. So as you go back in time, if you go to a high enough redshift where you're just forming the dark matter halos, then there's probably not going to be a lot of baryonic matter in those galaxies.
Mm-hmm.
And at the present time, if you can find things that look very relaxed, they've had enough time to pull in stuff, and it should be more consistent there.
Okay. How far we can go to say that it is approximately the same?
I don't know the numbers, but I think clusters, when you look at very, very relaxed clusters, people can go to redshifts of 0.5, 0.6, 0.7, and if they look relaxed and they look approximately spherically symmetric, omega baryons over omega total seems to be the same from cluster to cluster. And I don't know if anybody's done this on the scale of galaxies. I mean, for clusters, it's a little bit easier because you can measure omega baryons from the hot gas.
Okay. Okay, thank you.
Thanks.
I guess,
I'd like to ask you about the XCDM models. The lambda CDM is a particular case of the parameterized XCDM models, sure. But why do you usually investigate this model? Why these models are interested to you?
They're not that interesting to me.
That is not a dynamical
the dynamical
models, but why you, approximately in all your papers,
you use this model.
Investigate these models. Could you please answer?
It's because it's a very popular model for observers, and so it's kind of useful to have the same kind of constraints that you can compare with other people's constraints from these data sets that we look at. And it's used by observers because you can get closed form solution for the Hubble parameter as a function of redshift, and you can't do that in more realistic dynamical dark energy models with scalar fields. And it takes much more work to compare a more physically consistent model with a scalar field to observational data. So observers, because typically they'll use a single data set, and they don't get very strong constraints from a single data set, so I guess they're not that interested in looking at more physically consistent dynamical dark energy models like phi-CDM, because it takes much more work. But I'm not certain. I mean, you'd have to ask observers. I mean, the reason we use XCDM is because observers tend to use it a lot. And so we want to have some model that they can compare our results to their results.
Any questions? Okay. I think we are finished with question section. Maybe we say thank you once again to our guest.
Thank you very much.
Thank you.